Welcome. This video is going to be about improper integrals. It's not so much an integration technique as it is a particular scenario. And the scenario is when you have an integral that has one or more of the limits of integration as plus or minus infinity, or there is a value at or between those limits of integration at which the integrand does not exist. It's discontinuous. And you'll see both types of cases as I progress through this handout. And so that's when you have an improper integral. When that situation is encountered, what you need to do is convert it to a limit and then progress naturally. The one other aspect that I'm going to talk about in this video, you could see in the bottom paragraph here, and that is about convergence versus divergent integrals. Essentially, if the answer to an integral is a finite value, then the integral converges, and if it is not, then it diverges. And I'll mention that as we progress also. So let's take a look at the first example here. It is integrating 1 over x from 1 to infinity. So this is that first type of scenario where one of the bounds or limits of integration is plus or minus infinity. In this case, it's the positive one. And so I am going to restate this in terms of a limit. And I'm just going to use the value a, but you could use anything except x. So as a goes to infinity of the integral 1 to a of 1 over x dx. And now I am going to progress naturally. I'm just going to keep repeating that limit notation. So limit as a goes to infinity. The integral of 1 over x is the natural log of x, which I'm evaluating from 1 to a. And then I want to actually evaluate. So I've got the limit as a goes to infinity of the natural log of a minus the natural log of 1. And the natural log of 1 is 0. So this particular problem just simplifies to the limit as a goes to infinity of the natural log of a. Now, a natural log function, if you don't happen to have its curve memorized, looks like this. And so this is y equals the natural log of x. And so as a gets bigger and bigger, in other words, as we're going along the x-axis to the right, the curve is getting higher and higher, meaning that with respect to the y-axis, this is going to infinity. So since this is an infinite value, that means that the integral diverges. And let's take a look at problem 2, just so you get some more exposure here. And it looks very, very similar, except instead of 1 over x for the integrand, you've got 1 over x squared. And so the process is identical. This is the limit as a goes to infinity of the integral as 1 to a of x to the negative 2 dx, which is the limit as a goes to infinity. X to the negative 2 is, or the integral of that is negative 1 over x, which we are evaluating from 1 to a. And this is the limit as a goes to infinity of negative 1 over a minus a negative 1, which is going to be plus 1. And when you distribute the limit of 1 is a constant, so that's just going to be 1. So this is equivalent to 1 minus the limit as a goes to infinity of 1 over a. And so as a gets bigger and bigger, the denominator is getting larger, and so you're doing 1 over a bigger and bigger number, which that fraction is going to get smaller and smaller and essentially approaches 0. And so that's what the limit is, which means our answer is 1. And that implies that this integral, with the subtle difference of a power of 2 instead of 1, converges. Moving on, we have the integral of x e to the x dx from negative infinity to 0. And so here you've got the negative infinity sign. So that's what we're going to be switching out for the limit. So this is the limit as a goes to negative infinity of the integral a to 0 x e to the x dx. And you might use the integration by parts or the tabular method. I'll make use of the tabular approach, but integration by parts works fine. So I've got x and e to the x for my dv. The derivative of x is 1, and that derivative is 0. The integral of e to the x is e to the x, and the integral of that is still e to the x. And so if you haven't seen this before, the first cross product is going to be positive, the second one will be negative, and if you need more, it would keep alternating. So this means that this integral is the limit as a goes to negative infinity of x e to the x minus 1 times e to the x. And that is evaluated from a to 0. So when we evaluate, we have the limit as a goes to negative infinity. And at 0, x e to the x is 0, minus e to the 0 is 1, minus a e to the a, minus, but this is going to be negated and become a plus, e to the a. And so let's distribute the limit notation. So limit of negative 1 is itself negative 1 minus the limit of, or as a goes to negative infinity of a. So it's going to be e to the a, but I'm going to write that as e to the negative a plus the limit as a goes to negative infinity of e to the a. So the third one is pretty quick to see, and again, this is another scenario where it can be useful if you happen to know what functional curves look like. The exponential curve looks like this. And so as a, which is along the x-axis, becomes more and more negative, so we are going in this direction, we could see that the curve is approaching 0. So this limit is 0. Now, the first limit is a little bit harder to actually see. but I set it up to use a trick, and that is it's not clear which is growing faster, a or e to the a. But when you write it like this, what you see when you evaluate is you have negative infinity on top, and e to the negative infinity, or e to the positive infinity, is also infinity on bottom. And when you have an infinity over infinity scenario, you should immediately think of L'Hopital's. So that's what I'm going to make use of. So we've got -1 minus the limit as a goes to negative infinity. And L'Hopital's, remember you take the derivative of the top. A is your variable, so the derivative of a is 1. And the derivative of the denominator is negative e to the negative a. And that second limit is 0, so I'm just going to zero it out. And now when we take the limit of the 1 over negative e to negative a, you have 1 over negative e to the positive infinity, which is 1 over a really large number, which means that this term is also 0. And we are left with the answer of -1, which is finite. And so that means that our integral converges. And this brings us to our last example, which you'll notice does not have a plus or minus infinity, but one of the limits of integration is 0, and the integrand is discontinuous at 0 because you've got an x or a square root of x on the bottom. And so you'd be dividing by 0, which we don't like in the math world. So that is where I'm going to have the improper integral process come into play. So this is going to be rewritten as the limit as a goes to 0. And you could even do 0 from the right because no negative values exist for the natural log nor the square root of x. So, but it's fine to just leave it like this. But if you were being really particular, you'd have 0 from the right of the integral a to 1 of the natural log of x over the square root of x dx. So looking at this, it looks like integration by parts might be our way to go to solve this. So I'm going to let u be the natural log of x, and dv is x to the -1/2 dx, which means that du is going to be 1 over x dx, and v is going to be x to the 1/2 over 1/2, or multiplied by 2. And so now when we actually apply the integration by parts, we have the limit as a goes to 0 of uv, which is 2 root x natural log of x, minus the integral of v du and this will be evaluated from a to 1, and this will be integrated from a to 1. So we continue our process. We've got the limit as a goes to 0. And the first term is going to be 2 times 1 times the natural log of 1, which is 0. So that zeroes out, minus 2 root a times the natural log of a, minus, now we've got the integral, the x to the 1/2 over x, or x to the 1/2 minus 1, is going to be x to the negative half. So let me make a note of that this is x to the negative 1/2. That's how that simplifies. And so that's what we're integrating, which is going to be 2 times root x. And you still have the 2 constant up front, so this is going to be 4 root x, which we are evaluating from a to 1. So where does that bring us? We've got limit as a goes to 0 of negative 2 root a, natural log of a, minus, you have, and I'll do this in parentheses, we've got 4 times root 1, which is 4, minus 4 root a, almost there. So this is the limit as a goes to 0 of negative 2 root a, natural log of a, minus 4 plus 4 root a. And now we are ready to actually evaluate this limit. First term is possibly the trickiest, but I see we've got the square root of 0 and the natural log of 0. The natural log of 0 doesn't exist, but the limit is going to be negative infinity. And so the root a term is actually going to make this 0. Limit of negative 4 as a constant is itself, plus 4 times the limit as a goes to 0 of root a is going to be 0. And so we get an answer of negative 4, which means that this integral also converges. And so that covers a variety of scenarios where you have improper integrals and what you do. It's common for students to ignore the limit notation, but it's good practice and appropriate to actually make use of it when you have an improper integral. The only scenario that is not included in these examples is one where your integrand doesn't exist at a value between your limits of integration. So keep that in mind as you are exposed to different integrals. All right, good luck and enjoy.